Computers make no sense. You throw some metal in a box, supply some power, and suddenly you have a machine capable of rendering virtual worlds. Inside your PC is a central processing unit, or CPU. It is the central brain of the system, consisting of a piece of silicon packed with billions of microscopic switches called transistors. Depending on the flow of electricity, these switches are either pushed on or left off, exactly like a light bulb. Those two states give us 1 and 0. The value at any one of these switches is a bit, and it represents the absolute limit of the machine's native comprehension. It only knows if the power is flowing or if it isn't. This means that raw computer hardware executes billions of operations per second, but has no inherent logic or memory. It is a remarkably fast yet entirely ignorant piece of rock. If you had to manually track and flip billions of individual electrical switches just to type a single letter on a screen, you would go insane before finishing a sentence. To make these machines actually useful, we rely on abstraction. Abstraction is a structural design technique that slides a clean, opaque plane over the raw complexity below it, letting you use the system without needing to understand the underlying mechanics. The entire field of computer science is simply a towering stack of these translation layers. To understand how a computer really works, we have to climb this invisible tower, starting from raw electricity and working our way up to the global internet. On the first floor, we group individual bits together. Put 8 bits in a row and you have a byte. That single byte can hold 256 different combinations of ones and zeros, allowing the system to start encoding actual information, like numbers and letters. We can then wire these microscopic transistors together to create logic gates. These are electronic circuits that force raw electricity to follow the rules of Boolean algebra, a system for mathematical operations. For example, a current might only pass through if switch A and switch B are both pushed closed. By combining these gates, the CPU connects to RAM, a grid of temporary storage, and runs a continuous loop: fetch, decode, execute, and store. This physical loop happens exceptionally fast. A modern clock generator coordinates billions of these cycles every single second. At this foundation layer, we have built a machine that calculates at lightning speed, yet it still only understands strings of ones and zeros, lacking any real human context. To bridge that gap, we move up to the software layer. Here, we use a compiler. A compiler is a specialized program that translates human-readable programming languages, like C or Go, into the exact binary machine code the CPU requires. Once we have a language, we need a way to track information. We use variables, which act as a human abstraction to assign a recognizable name to a raw chunk of data stored in the computer's memory. Sometimes, instead of holding the data itself, a variable holds the physical address of where that data lives. This is called a pointer. It is a chunk of memory pointing to another specific location on the silicon. Managing these addresses carries physical consequences. If you try to touch memory that doesn't exist, you trigger a segmentation fault. If you forget to free up memory you are no longer using, you create a memory leak, which slowly eats up the chip's limited space until the program crashes. Software development is the active, high-stakes allocation of microscopic physical real estate. To prevent the system from collapsing under the weight of complex applications, all that random data must be organized into deliberate patterns called data structures. You might use an array, which is a continuous, locked block of memory slots that allows for fast retrieval. Or, if you need flexibility, you might use a linked list, which relies on scattered, floating nodes connected by directional pointers that can grow and shrink dynamically. Algorithms are step-by-step instructions designed to search, sort, and traverse structures. This graph visually demonstrates the danger of poor algorithmic efficiency, measuring how severely the required time or memory expands as the amount of input data grows. Programmers call this metric Big O notation. Without efficient data structures and well-designed algorithms, the sheer volume of modern data would immediately overwhelm even the fastest CPU, eventually exceeding its memory limits and triggering a stack overflow that halts the entire system. Moving higher up the tower, we reach human-centric programming paradigms. Object-oriented programming, or OOP, groups isolated data and behaviors into relatable classes that mimic real-world objects, making it easier to organize massive codebases. But sometimes humans cannot easily describe a problem with rigid code. Machine learning takes an alternative approach. Instead of explicit instructions, the algorithm is fed massive amounts of data and dynamically tweaks its own parameters to recognize patterns humans can't formalize, eventually identifying things like images of a bee. Finally, we scale out to the ultimate layer of abstraction, the internet. The internet is a vast network of computers communicating via rigid transmission protocols, where every machine is identified by a unique Internet Protocol or IP address. We often call this the cloud, but it is entirely grounded in harsh physical reality. Global data transfer relies literally on massive, thick cables lying across the bottom of the ocean. When you type a URL, your local web browser acts as a client. It sends a request across those undersea cables to query relational databases, systems that store data in structured tables, located on remote servers. A simple mouse click on a modern website is actually a physical electronic signal, traversing an ocean, filtering through a remote database, and returning the requested content to your screen in milliseconds. If we trace that single piece of downloaded data backwards, we drop right back down the tower. The signal travels from the ocean cables into your computer's operating system kernel, the core program that manages hardware and applications, and up into your local application. The application's instructions are fed through the compiler, mapped into the physical grid of the RAM, and ultimately executed by the microscopic flip of a single silicon transistor. None of this digital ecosystem is magic. It is a meticulously constructed, multi-layered ladder of human translation. By mastering these layers of abstraction, computer science allows us to turn a single bit into a global network, giving humans the ability to control physical matter with logic alone.